So that's the sound of katydids. Listen. In July, you may hear some fireworks too. I've got my window open. It's the 5th of July. Is it the 5th? I think it is the 5th. Yes, it's the 5th of July. And so there's still people out there using up their fireworks. But I wanted you to listen to the katydids because last night when I went to go put my chickens up, I've got an automatic door, so I really don't have to do it. But my chicken coop has a large back door, and when it's hot like this, I open it up so that it cools off. And after it cools off at nighttime, around 9:30 or 10, I'll go out there and shut the big door, just because it's so hot. Anyways, so I went out there last night, and my dog always goes with me, and he's always looking for a mouse or rats. They're always running around getting the leftover chicken feed, and he likes to go out there and try to catch them. He's not very good at it. But anyways, I walk around to the back side. So I have to go through my runner. It's got a door on it, like a gate. It's a chain link runner. And so I open up the gate and I walk through and I pass by the side of the coop, and then I walk around the back and I shut it up. And as I was coming back, I noticed that my dog isn't doing his normal routine. He's actually kind of just standing back watching. He's actually sitting. He's just sitting watching about 10 yards away from the coop. And I'm like, what is he? I actually said something to Hank. I was like, what are you doing? Because he's usually real excited, but he was being weird. Anyways, I hear a sound while I'm doing this. It's not the katydid sound that you typically hear. It's more of a cicada sound, and I don't have a clip to play you of cicada, but that's what it sounded to me, exactly like cicada. And I thought that there was a cicada that was trapped or something somewhere, and somewhere nearby. And so I'm like looking for it. I have a headlamp on. It's dark, but it's unusual for a cicada to be making sounds when it's at nighttime, as far as I know. Like I always hear them in the daytime. But anyways, excuse me. So as I'm doing this, the sound gets really loud, and it's like unusually loud, and I'm like, man, that's not a cicada. It didn't sound quite like a cicada. I was like, is that door? Is it my automatic coop door? It's got like a little motor on it that lifts the door up, and it does make a noise, but I thought it might have been broken or something, and I'm like shining my light on it and looking, and then I look down and I see about a 4-foot rattlesnake, literally inches from my feet, ready to strike. He is absolutely horrified, just as I am, and I just take a step back. Luckily, I had my handgun on me and I shot it. Now, I know that seems kind of rude to just shoot a rattlesnake. I don't know. Some people kill all snakes. I don't like to kill any animals. I despise killing animals. And something like a copperhead, I let go. But that rattlesnake, for some reason, I just shot it. I had my gun on me and I just pulled the gun out and shot it because I almost died. Like, that thing almost bit me. I don't know. If it had been in the daytime, I might have moved it. I might have caught it and moved it. I would never recommend anybody catch a rattlesnake. That's kind of idiotic, but I've caught hundreds of snakes in my life. I'm a hillbilly, so if I find something like a copperhead, I'll move it. Although I did kill a copperhead last year because my dog would not leave it alone, and I could not get my dog put up. So it was just the easiest thing to do, is just kill the copperhead before he kills my dog. So that's 2 snakes I've killed. Now, I've killed several when I was younger, but those are the only 2 that I can think of as an adult that I've killed. But they're recent. But sometimes you have to do stuff like that. And this year, I'm not feeling down on the rattlesnakes because I have seen and heard of people seeing at least about a dozen already this year. Like, they are out of control. I've only seen a handful of rattlesnakes in my entire life. And, these are all timber rattlers. But it's surprising. It's surprising how many there are this year. Anyways, it seems like there's a lot of stuff. Like I drove to the lake earlier, let my dog jump in, and there was 3 turtles on the road. Not in the same area, just at different locations. I had to dodge them. Sometimes I'll get out and move a turtle, but this is like a slow road. Hopefully nobody's going to run over them. Like, most people are driving pretty slow, so I kind of doubt they will. There was nobody out. I thought it was odd. So let's get to first principles cosmology. Sorry, I wanted to tell that story. That was it was impactful. Like, I didn't open the big door for the chickens today because I didn't want to have to come back out in the dark. Like, there's not much that I'm afraid of, but daggum rattlesnake at nighttime, that's scary. Anyways, let's get to first principles cosmology. I'm going to try to do this in a very precise manner, but if you've seen my other videos, this is going to be a lot of review. That's why I like to toss in little things like my rattlesnake story, because there's some people that watch every video I make, and I do that. I've got my own YouTube list that I follow, and I watch almost every video that some people make, and that's great. But I don't want to be boring. But I've only got basically one major topic that I want to talk about. Now, there are a few other things I want to talk about, but cosmology is by far my number one concern. So let's get to first principles cosmology. Sometimes I listen to myself, and sometimes I sound pretentious. And that's one of my least favorite things about people is pretentiousness. So I don't know why I sound like that. It may just be the way that I hear it. I don't know. But like, listen to your own voice. Everybody always says they hate it, but if I sound pretentious, I am not. I want you to know that I am I don't judge people. I'm not smarter than anybody else. I'm not some genius. I'm none of that. Like, I'm literally just, friggin' nobody. But I think I know what I'm talking about when it comes to this one very specific topic. So, I'm welcome. I'm like, why I'm doing this is for a peer review. That's literally the point of doing this. So, like I said, I'm going to try to be as accurate with my language as possible and as rigorous today. So here we go. First principles cosmology. What is first principles? Oh gosh, it's not even working. There we go. Now it should work. First principles are the fundamental concepts and assumptions from which a theory, system, or method is based. Okay? Everybody knows what first principles are, but it's like the most fundamental things about a subject. What are assumptions? These are things that we accept as true without proof. Sometimes it may not be possible to obtain proof or evidence. Evidence is different than proof. But assumptions can be made without evidence. And we all know what assumptions can do to us. However, you got to start somewhere. And when you're doing general relativity, cosmology, physics, when you're doing all of these crazy, wacky things, you've got to start somewhere. And so that's why you make assumptions. One of the assumptions I want to bring into question today is the notion of expansion/collapse. In the Friedman metric, the top two equations are the Friedman equations. The bottom equation is the line element for the FLRW metric. Okay, we're not going to go into detail on these, but it looks very complicated. But this is actually a super simple equation. I wouldn't say super simple, but it's pretty dang simple. It's a weird form. Now the line element at the bottom gets a little complicated, especially, I mean, regardless. There are assumptions within this metric. One is the notion of the scale factor, or the notion of expansion collapse. My dog is barking in the distance. Just a second ago, he just he's been laying here for hours. I start doing a podcast and he gets up and takes off out the door as fast as possible, and then just starts barking off at the edge of the property. It's like I could kill him right now. Whew, whatever. I don't know what he's barking at. Hold on. Okay, I'm back. Dude, it's been like 40 minutes. I totally forget what we were talking about. I've got the Friedman equations and the FLRW metric down below here. The point of me showing you these equations is just to mention that there is an assumption within the FLRW metric. There's this notion of expansion and collapse. Okay, this was in the original decisions. Of course, there was multiple people that came up with this one solution, but that's why it's called FLRW. But God, I'm so sorry. I just took a sip of coffee and it was very hot. But with this metric, there is just a basic assumption that the universe is either collapsing or expanding. And now you can't perfectly balance it. You got to fine tune all the parameters and everything. But the notion of expansion and collapse was just added to this to be able to demonstrate relativity. I mean, this was a possibility, and then after Hubble found the redshift, they assumed that it was expanding, because, I mean, the other option was collapse. And they found a redshift, so they went with expansion. But this is just an assumption. Now, of course, cosmologists will argue, and, there's so many people that will defend this assumption, but Today, we're going to pretend like the assumption is false. I don't like the notion, or the idea, the thought that the entire universe is either expanding or collapsing. Why don't I like it? Because the cosmological principle introduces this notion of isotropy. Now, they claim that expansion and collapse are isotropic. Honestly, no matter how you slice it, the concept of collapse and expansion within the FLRW they're different than the typical. Okay, so we have physics, we have Newtonian laws, and just things in physics that collapse and expand. There's all different types of things that collapse and expand. Within cosmology, or let's say astrophysics, we have stars and galaxies and stuff like that collapse and expand. Okay, they're massive bodies that collapse and expand. With all of these physical collapse and expansion concepts, the phenomena is caused by something. Okay? There is a causal relationship, and it's usually with gravity, especially when you're talking about cosmological objects collapsing and expanding, then gravity has something to do with it. The expansion and collapse within the FLRW are mystery Okay, they are mystery expanding and collapsing phenomenon. It is unknown what causes them. It's just an assumption that it's expanding or collapsing. We don't know why it expanded or collapsing, and there's all these other theories within the Big Bang, but this is supposed to describe the universe as it is today. This is a starting point. However, I believe that this assumption of expansion and collapse, I believe that it violates the isotropic portion, or the isotropy requirement of the cosmological principle. Now, we're going to get into this. It gets confusing because homogeneity is also a part of the cosmological principle, and I would like to claim that that is actually a false part, and it should not be part, but isotropy should be part of the cosmological principle. And I know this is madness, but let's go to the next slide. So instead of the assumption of expansion and collapse, what if we assume that the redshift is caused by gravitational redshift? So we don't have to worry about the FLRW metric. We can do it if we want. Like I'll get to that later, but we can use, we can just use the Einstein metric. We can just use any old static universe for our cosmological, for our general relativity metric. But we're going to assume that gravitational redshift is what causes Hubble's law, or the cosmological redshift. Why are we making that assumption? Well, because Friedman and everyone else made the assumption that the universe was expanding. So what's the other option? Well, there's only a handful of things that cause light to redshift, and gravity is one of them. So why not let's just assume for today, just for the moment, that gravity causes the cosmological redshift, just like Friedman and others have done. So this is the equation. This is the gravitational redshift equation, and HO on the left is Hubble's law. So this is what I'm going to try to prove to you today. Here is a more detailed description of more detailed equation for representing the gravitational redshift. So on the left you have the observer, on the right you have the emitter. You take the mass of both objects, the observer on the top, the emitter on the bottom, and that shows you the factor of change. It's fairly straightforward. 2 times gm divided by c squared r. So g is the gravitational constant, m is the mass of the object, c is the speed of light, 299,792,458 meters per second. R is the radius of whatever object you're talking about. Alright. The equation that I just showed you, this one, is not quite accurate. Okay? It's not quite accurate because objects are not alone in the universe. You are not alone as an observer looking at a star. It's not, there are other objects that interact with the field. So this is the true equation. And the little symbol that's in place of the 2gm is the gravitational potential. It just says the gravitational potential here versus the gravitational potential there. Okay? So in this image, imagine you have a planet like Saturn, and there's rings around the planet. And then you have 2 observers and an emitter on the surface of the planet. One observer is in between the planet and the rings. The second observer is far outside of the rings. Observer number 1, the first observer, the one that is on the interior of the rings, will notice less of a gravitational redshift than observer number 2. That's because the mass of the rings will also contribute to the gravitational redshift for observer number 2, but not necessarily for observer number 1. Of course, this all depends on relative position to other bodies and the distribution of the rings and the planet's mass. There's all kinds of things that go into this, but just as a general idea, I wanted you to understand how this works. It's not very straightforward in determining the gravitational potential at any given location, because you have to take the observer's perspective into account before you can do that. So the next slide, Jamie. I don't know if you know what that is. If you know what that is, write it in the comments. Next slide, Jamie. Okay, so here we have a bunch of planets or stars or gravitational bodies. They could be galaxies. Okay, let's think of them as galaxies. And we can place an observer anywhere in between them. Okay, these are gravitational bodies, and the brown space behind them is emptiness. Okay, there's just nothing there. So we have an observer in between. This observer weighs nothing, basically. It's basically nothing compared to the massive objects. So if the observer is looking at one massive object, now he's not looking through another massive object. Like there's space opening. There's a spatial opening, but this is what the distribution looks like if you made it in 2 dimensions. So you have to include the objects that are contributing to the observation, and that depends on the distance of the observer to the emitter. Okay, I call this the sphere of influence. It's actually greater than this, but I will show you because of the Schwarzschild metric and Birkhoff's theorem and things like that. Then I'll get into why this just becomes a perfect sphere. But for now, just understand that the observation is most influenced by the nearby gravitational objects, and nearby just means this objects between the observer and the emitter. Here's another example. Okay, the observer is further away, so there's more objects in the sphere of influence. The reason this is important is because we're going to get to work backwards from Hubble's law to find the density distribution of the universe. Okay, so we go back to this equation. Since we're going to simplify this, okay, we're going to say that an observer is somewhere in between galaxies. Okay, this observer is nowhere near a star or a galaxy. Okay, this person will be doing all of our observations. So the top part, there's no mass involved in this one, so we're just going to say 1. So this is always going to be a gravitational redshift, because this observer is at a unique place in the universe. He's not around any galaxies, okay? He's as far away as possible from any galaxies. And so we can reduce him to 1. Now, it's not exactly 1, but yes, it is. So, this right here is the Newtonian equation for gravity. Okay, this is just your basic equation for gravity. I want to show you a neat little trick that we can use to find the density distribution for this. The lowercase g stands for the gravitational acceleration. So typically this means the surface gravity of a planet or a star. Here we have the mass to density relationship. Mass equals rho 4/3 pi r cubed. Okay, straightforward. So we can substitute mass for rho 4/3 pi r cubed, and then it reduces to the gravitational constant times rho 4/3 pi r. Okay, and that's the new Newtonian equation for gravity using mass density. I like it. I like it better than the old one. Honestly, I don't like dividing. Dividing sucks. Multiplying's awesome. Dividing sucks. I don't know why I have this image in here so many times, but we're going to move on. All right, so now we can replace the gravitational redshift equation with this g, this gravitational acceleration. This 2gr is the gravitational 2gr divided by c squared is the gravitational redshift equation. It's just we're using density. This is a self-fixing density. I know it's a little confusing at first. Newtonian shell theorem. All this hopefully will come together very soon. I put a lot of time in placing these slides together. I have confidence that it will all make sense to everyone. We're going to see. I feel like I'm missing something between here and there. We're already at the... this is the Newtonian shell theorem, okay? Newtonian shell theorem is, it's not relevant in general relativity per se, but it's basically, essentially the same thing as Birkhoff's theorem. This is a great way to kind of visualize why things work the way they do when it comes to gravity. So you have a shelled mass, and then you have a test mass, which is M, on the outside of this shelled mass. The blue part is the shelled mass, and then there's also the gray part. The gray part is there's mass inside the transparent gray part that's outside the blue part. Okay, so that part exerts no force on the mass, but the blue part does exert force. Does this make sense? And the amount of mass exerted on the M is defined by R1. Now, if you had another test particle on the outside of this, like in the brown part, then it would be as if all of everything was in the very center. That would be R2. It would be all the mass within R2 was at the very center. So here we have three different observers. Okay, you have a massive emitting object in the very center. You have a cloud of dust, homogeneous dust on the outside of this mass. And then you have nothingness, okay? Observer 1, 2, and 3. Observer 1 sees the most amount of gravitational redshift. Observer 2 sees the second most. And observer 3 sees the third most. This is from the center. If you disagree with this, fine. Save it for later. Here's another example of this. Is just showing you the radii of influence. Okay, so you have a star and an observer. You have the difference between a star and a galaxy and an observer is a lot. Galaxies have higher amount of gravitational redshift. So if you have an observer in the same location looking at just a star, the star is going to have X amount of gravitational redshift. If that star is inside of a galaxy, it's going to have X plus whatever the galaxy is. So it's plus. That's it. My point in all of these slides is to show you the cumulative nature of gravity. Okay? Just the way that it works. It's cumulative. Especially when it's hierarchical, like our universe is structured. Back to this equation. This again, I don't know why this is here. Where are we at? Okay, so here we're going to insert the trick that I showed you with mass density into our gravitational redshift equation to find the so basically it's what we're doing. We're going to solve for the mass density. Hopefully this makes sense. So HO is the cosmological redshift, remember? And so the bottom equation, we can solve for the mass density. So as an example, let's say we're looking at a galaxy that is 1 megaparsec from us. In lambda cosmology, the Hubble constant would say that this galaxy is receding away from us at 72 kilometers a second per megaparsec. So at 1 megaparsec, it's accelerating, not accelerating, it's moving away from us at 72 kilometers a second. If we instead interpret that as gravitational redshift, and we want to find the density of the region having the radius r, which is the distance of light travel in this situation, the distance that the star or the galaxy is away from us, we can find the total density of that with this equation. This is our final equation to solve for, or to find Hubble's law, so 2GR, and it ends up being, and so this is our equation to solve for density, but this, if you work backwards from Hubble's law at 72 kilometers a second, now Hubble's law varies. It depends on which survey you're talking about. It could be as low as 40 something or as high as 70 something I've seen, or 80 something I've seen. It varies quite a bit. But like 72 meters or kilometers a second is not that bad. That's a pretty good average. I think it's a little high probably. I don't know. Could be low. We don't know. But if you work backwards from that, you end up getting this 3.5 times 10 to the negative 10 meters per second squared all throughout the universe. Okay? And this, the density, you can solve for density with this equation. R in this situation is the distance of light travel. When you do this, so all we've done, this is, let me just kind of rewind for a moment. I know it got a little complicated when I was talking about gravitational redshift, and some people may disagree with my interpretation of gravitational redshift. That's fine. Regardless, if you use the gravitational redshift equation and you solve for density, this is the density relationship that you get. Okay? So the bottom, the x-axis, is the distance in megaparsecs, and the y-axis on the vertical axis is in mass density. So as you can see, mass density is inversely proportional to the radius of the region you're talking about. To me, this is remarkable. Now, a lot of people can just laugh it away or ignore it, or get hung up on gravitational redshift or how it works or this and that. But this is literally the prediction you get from this, okay? This is far more accurate than the FLRW metric. The FLRW metric assumes that everything is this 10 to the negative 27 kilograms per cubic meter. And this shows that mass density is scale dependent, okay? So galaxies are more dense than clusters of galaxies. Clusters of galaxies are more dense than superclusters. So this mass distribution is actually more accurate than the homogeneity as assumed in the FLRW metric. And all we have done is assumed that the cosmological redshift is caused by gravity. And we are able to map out the distribution of mass. And this is relatively consistent with observation. I mean, you're talking at 2,000 megaparsecs, you're at something like 5 to the negative 25 kilograms per cubic meter. I mean, it's totally reasonable. And at, it approaches, it gets really high at, the lower densities. And of course, this is not going to be perfectly accurate, but this is more accurate than the current model, if that makes sense. Homogeneity is a false assumption. It's a false assumption because mass density is scale dependent. Mass density is scale dependent. It is not homogeneous. The universe has the most diverse. There is nothing. I don't know how to say this. There are basically all possible densities exist in the universe. If they're not possible, they don't exist, right? And so it's like it's the most inhomogeneous thing you can imagine. It's the opposite of homogeneous. But it is symmetrical. Okay, so that's the difference. There's a difference between homogeneity and symmetrical. Symmetry, between homogeneity and symmetry. And the universe is symmetrical, but it's not homogeneous. So that's what the cosmological principle would say. That's what the cosmological principle should say, is that the universe is symmetrical and isotropic. So this is our little trick added to, this is the equation for the Schwarzschild radius, okay? The Schwarzschild metric is, perhaps it's the most basic of metric solutions to the Einstein field equations. The Schwarzschild metric is it's basically just whatever a ball is, a motionless ball, a static mass, a round mass is the Schwarzschild metric. And so this is the Schwarzschild radius. The Schwarzschild radius is typically defined as the radius of an object if it were to collapse into be a black hole. So this equation utilizes the gravitational acceleration, which allows us to implement a density distribution into here. If you do this, the Schwarzschild radius of our universe is 13.6 billion light years. It's also the observable radius. Here is the equation again, just with mass. And I'm showing you the form here. We're just replacing mass with density. When we do this, and we work backwards, so let me go back to this. So this is the Schwarzschild radius equation, the equation to find the Schwarzschild radius. If we remove the mass, you notice we have to add the radius, which is kind of stupid. But the radius of the object we're talking about is different than the Schwarzschild radius. Okay? The radius of the objects we're talking about is it's like a hypothetical thing. It's like if we were talking about the Earth, the Schwarzschild radius would be much smaller than the radius of Earth, because all of Earth would collapse into a black hole. So the Schwarzschild radius of Earth would be much smaller than the radius of Earth. So that's why this R, that's why I wanted to show you this other R, the R cubed here. So if we map R to R using this, my uniform, uniform gravitational acceleration, and the density distribution that I've described so far, if you map R to R, you notice that the Schwarzschild radius is much smaller than the regular radius, all the way up into this 1.29 region, and then it surpasses. So essentially, the observable universe is a black hole. It's not a black hole per se, it's not a singularity, but black holes don't have to be a singularity. Kerr. Ask Kerr. Black holes don't have to be a singularity. You can have very, very large black holes with a low density. And that's what we have here. I feel like I've missed something. I need to go back. So let me just give you a quick review before we get into this next part. So what did we do? What have we done? Well, instead of assuming the universe is expanding, we dropped that assumption. Okay? We assume the cosmological redshift is caused by gravitational redshift. And that it would be 100% gravitational redshift if the observer was at a location of very low gravitational potential. That would be the starting point. And then we would find out about how much blue shift we would have from here and subtract. But to find out the very, very starting point, we use this equation. And this allows us to solve for mass density. When you do this, so I've assumed the cosmological redshift is 100% gravitational redshift. When you do that, you get a uniform gravitational acceleration. That is the density distribution. That's how much mass that would be required to form the gravitational redshift in the manner that I've described in this video. So that's what this chart is for. Not this one. Yes, this one. This one is the density to distance relationship. This one is the Schwarzschild radius to the actual radius. So it really doesn't matter until you get to the observable radius, and then it's the Schwarzschild radius. Now, why is that important? That is important because we have to choose a metric. If we're doing cosmology and we get rid of the FLRW metric, we have to choose a metric. So, what do you do if you just use the FLRW and just claim that the universe is static or perfectly balanced? It's neither expanding or collapsing. If you do this, and then you add this mass density distribution that I just said, it reduces to the Einstein metric. So you're just basically back to the Einstein metric. Now, in my opinion, again, this is my opinion. I am not an expert. I am a hillbilly YouTuber, okay? But in my opinion, the Einstein metric, when it's symmetrical, as in the observable universe, like if anything is symmetrical, the observable universe is symmetrical. So when you have symmetry, there's something called the Birkhoff's theorem, okay? Birkhoff's theorem just says that it reduces to the Schwarzschild metric. So instead of the Einstein metric, we have the Schwarzschild metric. And then this is the Schwarzschild radius of the Schwarzschild metric. The Schwarzschild metric is where the gravitational redshift equation is derived from. To me, this is remarkable. It's absolutely, like everything that I've described to you so far is convincing to me. Because this is not only more accurate than the FLRW, but it makes more sense because the Schwarzschild metric is the metric. I mean, it is the metric, okay? And if the universe is symmetrical, as in the cosmological principle, then we should be able to use the Schwarzschild metric. But when you have the Schwarzschild metric, there's another phenomenon that I want to talk about. The Schwarzschild metric gives rise to something called Hawking radiation. Now, Hawking radiation is a form of black body radiation. The temperature of this black body radiation can be predicted with this equation. If you do this for the observable universe, it comes up nowhere near the temperature needed to get to the 2.7 degrees Kelvin or whatever it is in the cosmic microwave background radiation. It's nowhere near enough. However, let's think about this. If the universe is described as a Schwarzschild metric, at the Schwarzschild radius, there should be black body radiation. This black body radiation is emitted at a region of the universe that is beyond the observable radius, or is right there at the observable radius. It is the observable radius. The location. This would define the location of the observable radius, I think. But regardless, this is the light is generated by quantum mechanical effects. It's not generated by stars. Okay, it's generated by quantum mechanical effects. And this black body radiation just manifests within the metric. So, it's not gravitationally redshifted, because it's not released by a star. This is the opposite. This light is gravitationally blue shifted, because we are inside of us on a planet, inside of a galaxy. And so, light that is released from empty space is going to be blue shifted. How much is it going to be blue shifted? It's going to be blue shifted again by the entire observable universe, because this is beyond the observable radius. So this would be the maximum amount of gravitational blue shift that you could have. This is the maximum factor of change. I thought it was interesting when I first started researching the maximum factor of change. Like, you would think that someone would, at least for the Lorentz factor, the factor of change within special relativity, you would think that somebody would have at least hypothesized or at least contemplated or talked about, even on a forum somewhere, about the maximum factor of change. But nobody's ever said this. Like, everybody just says that it approaches infinity, but there is a realistic maximum upper limit to the factor of change. So I thought about this. How would you calculate it? It's tricky. This is a tricky one to think about. How would you calculate the maximum factor of change in relativity? Well, this is what I came up with. I'll just explain this. This is Planck length, okay? That's what the LP is. And the RS is just the Schwarzschild radius. And so this is basically like the smallest possible, like the closest to the speed of light that you can get if it was special relativity. But this is general relativity, so it's like the gravitational potential reaches, like it's so close to the light speed that, it's 1 Planck length more, and 1 Planck length more, and it surpasses the speed of light, and that's the observable radius. And so at this location, this is the 1 Planck length limit. If you do this and then add that to the temperature equation, then you can pretty well get the cosmic microwave background radiation temperature. It's close, okay? It's close. And again, I'm not an expert. This is just my guess. I don't know. I was hoping somebody else would help. I'm still doing all this by myself. I've not even had a proper peer review. People make comments and have, give me some advice and said things that really were unrelated to the things I'm saying, and that's hurtful. But let's go to another topic. So, modified Newtonian dynamics. Modified Newtonian dynamics is this idea that there's an alternative explanation to dark. Instead of dark matter, they're using modified Newtonian dynamics, which is just a modified form of Newton's laws. And so the idea is that it's not these. So dark matter, the reason that they think that there's dark matter is because there's a flat rotational curve in spiral galaxies. In other words, the stars on the outside of the galaxy are they're moving at a faster rate than they should be, or they think they should be moving faster. So according to their calculations, the stars should be moving faster as you get closer to the edge of the galaxy, but they're not. It's a flat rotational curve. They're moving the same speed all throughout the most of the galaxy. And so it's like, why are they doing that? So of course, academia, all the Ivy Leaguers, they all said, it's dark matter. Obviously, there's an invisible mass. There's an invisible exotic substance that just, it's 60% of the friggin' universe or something, and it's just out there. And so that's why we can't figure out the right speeds of these stars in these galaxies. It's because there's an exotic substance. But some smart people out there said, there's a way we could just modify the equations and then see what comes up. And this is the result. This 1.2 times 10 to the negative 10 meters per second squared. It's basically a uniform gravitational acceleration. So it's not uniform. Okay, let's say it's minimum. That's the right word to use. I always say uniform, but it's actually kind of a minimum. It's like you can't go lower than this. You can't have 0 gravitational acceleration. It's got to be at least 1.2. Okay. Now this for MOND, all of these, the discussion about this dark matter stuff here in galaxies and spiral galaxies and the rotational curves and modified Newtonian dynamics. These are all close observations. These are all observations well within a megaparsec. Okay, like these are observations that should be affected by the local neighborhood. Just the gravity in this area is not symmetrical. The distribution of mass in the local neighborhood is not symmetrical. Any local neighborhood, in other words, any cluster region of galaxies where you're talking about a few hundred clusters, it's not going to be symmetrical. Like the image I showed you earlier with the balls, this is not symmetrical. Okay, wow, that was a long time ago. This is not symmetrical. The reason that I have the red sphere here is because with Birkhoff's theorem, you can say that it becomes symmetrical. Okay, but Birkhoff's theorem, symmetry is required for Birkhoff's theorem. However, Birkhoff's theorem does, like, it becomes more and more accurate with more symmetry. So it's not just all or none. Like, Birkhoff's theorem is, a great way to think about this stuff because it's really close. Like, obviously it depends on the distribution of each individual observation and the relative positions of all the bodies. But with Birkhoff's theorem, it approaches this with symmetry. So if you're talking about cosmology, it's very important to think about Birkhoff's theorem. And Birkhoff's theorem basically states that the FLRW metric, because there's an observable radius and the universe is symmetrical, then it reduces to the Schwarzschild metric. And it doesn't matter if it's expanding or not. There should be a gravitational redshift that is distance proportional to the distance of light travel. This is my interpretation of the field. Okay, I have only read, few dozen books but these are all the best books on the subject. I have only studied this for a good 15 years now. You know, honestly, like somebody's got to give me something solid, because I think that this is a totally 100% legit cosmological model that should supersede lambda cosmology. Okay? We're getting really, really close, because this, look, all I've done, the only thing that I did was say, I don't believe the universe is expanding. I don't believe it. Okay, so I doubt that. Is that okay to do? Is that okay? According to Sean Carroll, that's not okay to do. According to Sean Carroll, you're an idiot if you do this. But I doubt it, because it doesn't make sense to me. Why would the metric expand? See, typically expansion and collapse have causal relationships. There is no causal relationship to the expansion and collapse explained in lambda cosmology. The expansion in lambda cosmology just is. It's also anisotropic, okay? So I think that the cosmological principle should be redescribed as the universe should appear symmetrical and isotropic to all observers. Okay, symmetrical and isotropic. Not homogeneous, symmetrical. Because the universe is not homogeneous. It should appear symmetrical to all observers on the largest scales. Okay, we're talking about the largest scales. But with that said, the FLRW metric, the expansion within the FLRW metric, and the collapse within that, those are anisotropic phenomena. Okay? They are, all you have to do to prove this is rewind the universe. So if you rewind the universe, it collapses to a single point. That is anisotropy. Okay? That means that, 20 minutes after the beginning of the universe, if you have an observer, the universe is not going to be isotropic. So when does it become isotropic, according to the FLRW? Regardless, all we've done in this video is assume the universe is static, and that the cosmological redshift is caused by gravitational redshift. Then, working backwards from Hubble's law, we obtain the density distribution, which is this 3.5 times 10 to the negative 10 meters per second squared gravitational acceleration. This is like it's the minimum. So if you take the observable radius of the universe and all of the mass in the universe, and you plug that into the Newtonian equation for gravity, you're going to get that 3.5 times 10 to the negative 10 meters per second squared. And so there is no region in the observable universe that can be lower than that. That is the minimum gravitational acceleration. So does that make sense? Let me just go back, and just so you can visualize it, let me see if I can find there it is, the beautiful equation for Newtonian gravitational acceleration. If this m is the total mass of the observable universe, so it's something like, I don't know, I think I use 8 times 10 to the, is it 52 kilograms? I think that's right. I may be wrong. But, and then the gravitational constant divided by like 1.29 times 10 to the 26 meters, something like that, 13.8 billion light years. So if you use that, you get 3.5 times 10 to the negative 10 meters per second squared. That would be the minimum gravitational acceleration throughout the entire universe. Now, obviously, local distributions It can change. But that's where this modified Newtonian dynamics comes from. It's different than the measurements that Milgram? It's different than what Milgram discovered in his observations, but he was, like I said, he was looking at galaxies that are relatively close. Over the course of the entire observable universe, it's going to become more symmetrical, and so it'll be different. I don't know why his minimum threshold is different than this. I don't know. It's complex, but to me, this is a much better. It's a much better model than lambda cosmology. Now, obviously, it needs a lot of testing and eyeballs, but this is just me. I can't do the work of millions. But trying to find. Here we go. So all we did. I know I've said this a million times. I'm trying to wrap it up. All we've done is assume the cosmological redshift is caused by gravitational redshift, and then we derived the mass density, which is scale dependent. That's what's amazing about it. It depends on the scale. So it's scale variant. It's inversely proportional to the radius. It becomes more symmetrical at scale. That's another assumption we make. But it's a very safe assumption. Symmetry at scale is, this is a well-known phenomenon that is agreed upon. And so that Birkhoff's theorem becomes more and more applicable at scale. All metrics reduced to the Schwarzschild metric at scale. Okay? All metrics reduced to the Schwarzschild metric at scale. Everything goes to the Schwarzschild metric. The Schwarzschild metric is tired light. Okay? Hey, and this is a modified version of the Schwarzschild metric. It's not the original Schwarzschild metric. I've had conversations with people that said this is not the real Schwarzschild metric because density is not homogenous throughout it. I don't see why that's a requirement. The density in this is inversely proportional to the radius. It's still the Schwarzschild metric. Everything still works out. Okay? And then the minimum threshold for gravitational acceleration is what this MOND constant is. And I think this is the source of the issue and why we come up with dark matter. But if you do, and then the CMBR is blue shifted Hawking radiation. Maximum amount of blue shifted Hawking radiation. That's my model. It's better than Sean Carroll's. It's better than MIT's. It's better than Friedman. It's better than Hubble's. It's better than Neil deGrasse Tyson's model. It's better than everyone's model except Albert Einstein. And it's essentially the exact same model as Albert Einstein. The only thing different is that I worked backwards from Hubble's law and assumed the gravitational redshift to find the density distribution. When you do this, you can use the Einstein metric. It just reduces to the Schwarzschild metric. Because it's a spherically symmetric shelled mass. That's what the observable universe is. It is a spherically symmetric shelled mass. I don't know. I honestly don't think that people. The problem. I've had a lot of people say, why don't they do this? Or why don't the experts say this? Why are you having to do this? And I've thought long and hard. I wanted to find something. But the truth of the matter is, no one has rolled up their sleeves and done this except since Einstein. Okay, now Hawking did some stuff, but everyone else has been focused on expansion. They were convinced of expansion. I don't know why. Something about expansion was thrilling. But when you roll up your sleeves and you just do stuff, you find stuff. And all I've done, again, the only assumption here is that the gravitational redshift is caused by the cosmological redshift, or the cosmological redshift is caused by gravitational redshift. I think I'm repeating myself 100 times, so I think I'm calling it. Have a good night.